Okay, so please. Okay, so thank you very much for the invitation and for the introduction as well. It's always great to be back in Luxembourg. I'm going to talk about implicit machine learning today. So in this workshop, you will be hearing a lot about how to make machine learning force fields more accurate and more transferable and more broadly applicable across chemical space. And in this talk, I'm going to talk about how to translate that progress into longer simulations on longer timescales. And just briefly to define the word, so implicit models, what are they? So in a nutshell, traditional explicit machine learning force fields, they have a data loss in the loss function. And implicit models, they add or replace the data loss with a consistency criteria. And I will tell you more about what specifically this means. And I will show you two ways of how to use implicit modeling in order to accelerate MB simulations. But before that, I want to acknowledge all the great people that I work with in Klaus Robert Müller's group. They are very talented and very driven and come from all kinds of disciplines, and it's going to be their work that I'm presenting today. And Joshua Futterer, he's here. I don't have an image yet. He joined quite recently, but you can see him in person. And of course, there's also many others. Now, before I get going with implicit modeling, I want to show this image. It's going to be probably the most shown figure today. Alex, he taught me how to appreciate it because it really tells many stories. And so this is from a review that we wrote together with Klaus and Alex back in 21. And back then, we kind of took account of the state of the field, and what was possible back then was already quite amazing. So we were able to do small biomolecules, small molecules in gas phase, maybe small peptides, so generally systems up to 1,000 atoms roughly. And this was only 5 years ago, and nowadays we can do, on a single GPU, we can do hundreds of thousands of atoms. And this progress is way faster than many had anticipated. So it's really amazing how far we've come, and I have one little demonstration here that is preliminary work. This is work that Joshua is doing with his next generation of the Socrates family of force fields. So what you can see here is this protein that's called aquaporin, and it's embedded in a lipid membrane in this animation, and it's surrounded by water. And it's actually it's interesting because it's a functional kind of system, so it's doing something, and in particular it's transporting water, individual water molecules along those narrow channels. And remarkably, this model has been trained on the SPICE data sets, on a data set of small fragments. It has not been specifically trained to predict this, and yet it still works. So this is more of a scaling test now, so we just wanted to see if we can scale it up to this system of 90,000 atoms, but it's already also behaving in the way that we expect, that we would expect, and we are also investigating whether it really is correct in the strict sense. And remarkably, each of those frames here only takes a few milliseconds to predict, right? And actually, in the hands-on session, I don't know if we got this going, but we have this, those models are so fast now that they run in a browser, so you can actually play and interact with live MB simulations. And Joshua can help you with this in the hands-on session later. So you can build your own atoms, and you can learn some chemistry along the way. And this is, so the models are fast enough to run even on a CPU now. And then you can play around with it, and it turns out that you can get a really good intuition for how different force fields work. So we tried this with two different force fields, and they all feel kind of different. Okay, but so I want to just go back to appreciate how good force fields are. So nowadays, the modern force fields, they're all linear scaling, so they only differ by the number or by the prefactor, right? So they all scale linearly, and our newest model is the newest ones are usually the fastest ones. So it has a little lower prefactor, and that's really quite remarkable because it goes against contemporary complexity theory that we know from computer science, right? So we know that the many-body problem is an exponential problem, and even in approximation or for systems that are not strictly correlated, it's polynomial, right? And of course we know this from traditional electronic structure methods. Even the best ones, they still scale polynomially like DFT. And yet we can do this even on the atomistic side with machine learning. We can do this in linear time. And the reason is that it turns out that for a well-defined system, we can actually parameterize the space of solutions in linear time, right? So this kind of goes against traditional complexity theory because we're actually solving a different problem. But I want to look at MD or at the prediction of forces in a much broader context now, because I think we're at an interesting crossing point. So if you look, I mean, the prediction of forces is not a means, or it's not like the final goal. The final goal is to use it in this pipeline where it's being used in MDs, and then to eventually sample from the Boltzmann distribution. And we didn't really, in this computational chain, we used to ignore the simulation part because it used to be the cheap part, right? But nowadays, we're at this interesting crossing point where the cost of force computation, being linear, is the same cost or in the same complexity class as the simulation of the cost of the simulation, right? And of course, the simulation also scales with the number of steps that we need to take, and they are limited, and we are limited by the highest frequency in the signal. So we need to take many, many steps in order to integrate over long time scales. And for biomolecules like proteins, they can be on the millisecond scale, and that means that we, for this femtosecond step size or resolution, we need trillions of steps. And so the step size really, or the length of the simulation is really the limiting factor. So I want to propose to look at this problem now that both of those two components, the simulation and the force prediction, are at the same complexity class. So we should really look at this problem as a joint problem now to try to see whether we can eke out some more performance here. And traditionally, this, of course, with traditional methods has been done before. So if we look at physics-inspired approaches, how can we accelerate MD simulations? One of the things we could do is we could, for example, freeze some degrees of freedom, removing hydrogens, for example, that removes high frequencies from the signal. Therefore, we can choose a higher integration step, right? So that gives us efficiency in how we can run the simulation, but we, of course, alter the system that we're observing now. Along the same lines, we could do coarse graining, where, again, we summarize particles into heavier ones, and therefore high-frequency signal components are removed from the signal, so we can integrate with larger steps, and also now we have less particles. So again, that lowers the t factor and the n factor in our complexity computation. And then on the other extreme, we can say, well, maybe we are not even interested in the dynamics, we're just interested in the final result in the Boltzmann distribution. And then we can go to, this works on generative modeling, where the Boltzmann distribution is directly predicted using machine learning, and that eliminates this simulation component altogether. But of course, we also lose all the dynamic information, right? So this is the other extreme, and it turns out that there's little middle ground from a machine learning perspective between those two. So I'm going to talk about two examples from that lie roughly here on the spectrum, right? That retain some or all of the dynamic information, but are still faster and using the temporal coherence. And so the first example is implicit machine learning force fields, and it's really motivated by the realization that if we cannot make machine learning force fields any faster, since they're already in this O of n complexity class and there's not many classes below it, can we at least reuse computations across the MD trajectory to make it more efficient, right? Because there's a lot of redundant work. And for that, we must move away from the way we used to construct graph neural networks, to this new implicit way. And I'm going to illustrate this. So just to remind everyone, all machine learning force fields are nowadays are based on graph neural networks, and in a nutshell, they are based on this this principle. So we have a series of individually parameterized layers, F, usually like a message passing layer, for example, and starting from an initial configuration that usually encodes the composition of the system. It then, using the geometric information, builds a latent representation of our graph in some compressed space. And this takes several layers, and then we end up with this graph representation H here, and then we plug it into a very simple, it's usually, or it can be a linear readout layer, or sometimes it's a small neural network, and that returns our property that we want to observe, like the energy or the forces. Now, on the other hand, implicit models, they only use one layer, right? So they only one layer F, and we now define the result not as a fixed sequence of steps, but we have a self-consistency criterion. In this case, we say that we have reached the final embedding if we have reached a fixed point, right? Now, this means that the number of layers is of course flexible, and also it depends on where we start, right? How close our initial guess is to the solution. Okay, now, so this general principle is in the wider machine learning literature is known as deep equilibrium models, or more generally as neural ODEs, right? And we're using this here to create force fields. So there's some conditions that have to hold on F in order to really make the fixed point exist and also make it unique. I will tell you more about this, but it turns out that we can actually turn any existing machine learning force field that is explicit into an implicit one. But in a nutshell, those two approaches differ by this property, which is that the implicit neural network can be started from any starting guess for the final graph representation, and the explicit network always has to start from the initialization that we have to use when training the model, because it's rigidly defined. And I think you can probably already see where this is going. So you can see here, this is a MD trajectory in the latent space. So each point is one of those, it's a graph embedding, and it's smooth, and we know that it's smooth because actually the embedding is a differentiable function of our geometry, R, right? So if the geometry only changes a little between steps, so are the embeddings. So this kind of suggests this idea already that if we have, in an MD trajectory, if we have computed the embedding for one particular graph, and then it changes only marginally in the next step, then this prior embedding would serve as a very good initialization for the next computation, right? And a fixed graph, of course, a fixed neural network, an explicit neural network nowadays still has to do the full computation. It cannot use this redundancy in the structures that we have here over time. So let me actually zoom in onto this trajectory. Here again, you see the same trajectory. It's a bit simplified here. And I'm going to focus on the first 3 points here in our initial MD trajectory and tell you more about how implicit models work. So at the very bottom, you see the first MD step. And each layer represents the fixed point equation that the implicit neural network imposes. It's different in each time step because it depends on the geometry, right? So it's a bit different. And in the first, so the lower time step, in the first time step, you can see that we have no initial guess or no good initial guess. So we start from a generic solution, and it takes us several steps to reach the fixed point, right? And then we have it, and then we can apply the readout layer and get the energy and the forces. Now, already in the second equation, in the second iteration of our, or the second step of our MD simulation, we can use our previous solution and actually warm start the iteration. So you can see we are much closer to the fixed point now. And now in this example, it only takes 2 iterations to reach the fixed point. So we already amortized some of the cost along this trajectory. And now we can actually continue this principle, and we go into this first MD step, into the third MD step. So that's the top floor of the stack plot. And now we have 2 past embedding. We have the information of 2 past embeddings, converged embeddings, and we can actually interpolate between them. So now we have a higher order interpolation. So it's a linear interpolation in this simple case. And this way we get even closer to the true solution, right? So now we have a starting guess in the third MD step that is very close to the solution, and it actually only takes us 1 more step to converge, right? So we effectively apply a model that only has 1 layer. So it's not a deep model, but it acts like a deep model. And there is actually some caveats, some secrets to this, which is that we are interested in derivatives. And this is getting a bit technical now. So if you're not interested in how to compute derivatives in implicit modeling, you can zone out for 3 slides now. Okay, so I have a bit more a calmer color scale now. So again, so implicit modeling, in a nutshell, you have this self-consistent equation, generate the embedding, and then from that we get the readout. And the issue kind of is that if you would, it's a sequence of layers still, even if the same is reused. And now if you would like to use backpropagation to compute the derivatives, so for example the force of this sequence, then of course you would have to step through all of those computations, which means that everything that you have gained by warm starting, you would now lose by computing the forces. Okay? But luckily there's something that can be done about it. So if we define our F to be not only dependent on the current embedding, but also on the geometry, on the current geometry, right? So this is a small change that we have to do to some machine learning, explicit machine learning force fields in order to make them implicit. So if it depends on R, then we can actually rearrange the expression for the forces like such. And if we look closely, this first part is actually a linear system, right? So if we solve this, we solve the equation for the forces. And we can write this as a numerical, so it's an iterative scheme, right? As a numerical expression. And this again is another fixed point equation, which means that we can not only start our iteration for the latent space embedding, but we can also start our this other vector v star here. We can also warm start it in a similar way. So for example, we could do a constant or a linear warm start, as you've seen previously. So we actually, in implicit modeling, we have 2 fixed point equations. One for the actual embedding h, and then this other vector v that we can then use to generate very efficient forces. And it turns out that both of those equations can be warm started very, very efficiently, usually within 1 or 2 steps, right? So yeah, both the forward and the backward pass, they work. And now, as I said, this is applicable to many architectures because it's an extension of existing architectures. And so we applied it to this pane machine learning force field here. And the first question that we needed to ask is whether the implicit approach can be as accurate as the explicit approach, because after all, we're using way less parameters, right? There's only 1 layer that we need to parameterize, whereas traditionally we have up to between 3 and 5 layers that all need individual parameters. The implicit model only has 1. So we iterated an implicit pane up until convergence, and then we checked how many explicit layers do we need in order to match the accuracy of the implicit model. And in the case of pane, we need about 5 layers. And then we did it for 2 other architectures, like this generic equivariant SO3-net architecture. Here, actually, the explicit SO3-net already matches the implicit model with 3 layers, but it's still 3 more than 1, right? And for Schnedt, it's also 3. So we get the performance of multiple layers for the cost of a single one. Now, this is not the whole story, so we need to answer a few more questions. One of them is, if we convert an explicit model into an implicit one, do we actually lose some of the good generalization properties? So we try to answer this, or I illustrate this, our analyses on this simple example of alanine dipeptide here. And you can see the training data in those contour plots. And current neural networks, they can extrapolate from the known training data into this other area of phase space, and we verified that the implicit variants can also do this, right? So we're not losing any of the good properties of the explicit models. And then there's a few additional observations that we can make here, which is that if you look at the purple plot in the middle, whenever we go far away from the training data, usually to conformations that are a bit more difficult, the model takes more iterations. The implicit model takes more iterations, which means it evaluates the layer more often, because those geometries are more difficult and are not, the starting guess is not as good. So it actually spends compute where it's necessary, and then close to the training data where most of the MD spends the most time in, it actually uses very few iterations. And now if we go from purple to green, you can see that now we turned on warm starting using linear interpolation in this example, and you can see that across the majority of the phase space, we actually only need on average about 1.1, 1.2 layers, which means that again we are performing at the accuracy and other properties of an explicit layer, but we're actually only evaluating a single layer network effectively, because we can reuse the information over time. Now, this is another test. So what happens if we increase the temperature in our simulation? Obviously, the conformations that we visit, they become more diverse, which means that it will be more difficult for the network to get answers, to compute those, and we can observe that indeed the network actually spends more iterations. When we increase the temperature to get the answer, it's still going to be accurate. And again, if we apply warm starting, we can lower the number of iterations in all of those cases for different temperatures. Now, how about the efficiency? So it turns, we have this. In order to evaluate the implicit network, we need to solve in just a self-consistent equation. So now the question is how well do we have to actually solve it in order for this to work? Because if we solve it to a very high accuracy, then obviously the answer will be good, but it's going to be expensive because we need more iterations. Or we can allow a higher error, so have a looser tolerance, and then we have less iterations. So we investigated what happens if we loosen the tolerance, and what we observe is that it increases the energy drift, obviously, in the simulation, because the model will not be as accurate, but it can be easily counteracted by the thermostat, right? So we can kind of loosen the tolerance to get more performance, and then turn the thermostat a little higher, or we can tighten the tolerance, and then the thermostat doesn't have to work as much in removing the errors that the model is giving. And then we tested the stability of MD simulations for different configurations. Okay, so this was implicit modeling. Now I want to go to another also implicit approach, where we no longer separate the generation of forces into simulation, but now we're and then using temporal coherence to gain efficiency. Now we're actually really combining both steps into one. And this is Hamiltonian flow maps. So just to define it, a Hamiltonian flow map is this function, we call it U here, that predicts next time steps, right? So for a given, so this function U takes the positions of a system and the momenta, and then this time delta t, and then it gives you the configuration after delta t. So it's a configuration in the future. And we can do this depending on how we define this delta t. We can skip to the next MD step, but obviously, in principle, this definition allows us to also skip further in the future and leapfrog steps. Now, the general idea obviously exists, so this is not new, and even machine learning implementations of this idea exist. And there's broadly speaking, two different classes. One of them just takes a configuration, a phase-based configuration of a system, and then outputs directly the following MD step. So this is a huge class of models that does it this way. And then a more recent development is to actually do this leapfrogging. So arguably this is more useful, right? So you don't predict the immediate next step, but you can predict steps in the future to some extent. Now, with both of those, and here those references are just examples, so there's way more work than I'm showing here. Now, one big downside that makes those approaches impractical, of course, is that you need the future time steps as a data label, right? So from a machine learning perspective, this is not too exciting, because those models they're just trained on future labels. So obviously, graph neural networks, they can do this, and those works show that it's indeed possible. But you need future labels, and this is a huge limitation, especially in the context of this general purpose machine learning force field summer school, because as you all know, I mean, in order to have those future time steps, you would need to compute them on your own. So some works do this. For each geometry or for each system, you would need a short MD trajectory, for example, that would give you this temporal correlation over time that you need in order to train your model. So this means, in practice, you need to generate your own data sets. But as we all know nowadays, usually the data sets that we train the general purpose models on, they are a mixture of many existing data sets, like for example QCML, OMO, SPICE, and so on. And they already exist, and of course we would like to use them, right? So we don't want to rely on our own data, we would like to use the existing data sets. Only this would really make Hamiltonian flow maps useful. And so we set out to construct Hamiltonian flow maps that don't need trajectory information. And I'm going to walk you through how this is possible. Okay, so we start with this function u bar. And it's defined as, it's a function that predicts the mean, momentum, and force after a given time step delta t. Right? So it's defined as the integral over the momentum and the forces over this time integral, starting at our initial position x. So x is the geometry and t for the momentum. And if we had such a function, then we would be able to define a Hamiltonian flow map as specified in the previous slide, just using one single integration step. Right? So we take our initial position and then multiply the mean with the time step, and this would return the future position. And this u bar, we're going to parameterize it using a neural network. Right? So it's going to be a neural network that predicts the mean momenta and the mean forces. So, and we're going to do this using this loss function, and I'm going to work you through it. So you can already see that this loss function is a self-consistent loss, because this function u bar that's the model we want to reconstruct, it also appears as a label in this stop graph condition. Okay, so it's kind of learning from itself anyway. What is this u target? So what is it really learning from? So this u target can be derived from the total energy, total time derivative of this mean displacement function in the first line, right? So you take the total time derivative and you rearrange a bit, and this gives you this u target. Now, what is it really doing? So you can kind of think of this time derivative of u as it's a derivative along the phase-space trajectory of the system, right? So it's kind of collecting something along those time trajectories. And this is inspired by this mean flow work in generative modeling, where they try to make more efficient generative flow models that also have this issue that they have to do very expensive simulations during inference time. And so they also want to kind of shorten this and do this in fewer steps. But here it's applied to MD. Okay, so let's look at this together. So what makes this loss function special? First of all, if you look at all the inputs that it uses, it only depends on the positions and the momenta and the forces at the current time t, right? So in a sequence of geometries, or so we don't need the sequence, we only need to know our positions, momenta, and forces at our current time, because that's all the information that enters our loss function. Okay, so that's already good. Now, secondly, we have those derivatives in there, which also, in a way, also look into the future. But and they are potentially expensive, because having derivatives in a loss function always means that you have to then again differentiate through them. So you have a second derivative when you train the model to do the backpropagation. But our derivatives, they only appear in this stop grad condition, which is what it means is that gradients are not followed through there, and which means that there's no second kind of pass during training through those derivatives. And the derivatives themselves can be efficiently computed using autodiff, using Jacobian vector products very cheaply. And the third aspect is that we have to sample from different time steps, but we can simply sample uniformly. They have no other meaning other than saying that each phase space sample can appear at any time point in different trajectories, right? So we can simply, so that's not hard to sample from t, right? We can simply sample from our interval, and it's limited by this maximum time horizon that is determined by the onset of kind of chaotic behavior in RMD. So it's usually quite short, but it's still very still higher than the initial high resolution MD time step. So using this function, we realize this dream of having Hamiltonian flow maps that don't use trajectory information, right? In principle and also in practice, it can be trained on existing data sets, because it uses the same training data that machine learning force fields do, yet it can kind of look into the future. Okay, so, and then we applied this first to two test systems. So those are those classical test systems, this Barbanes potential and a spring pendulum. And we investigated two different large time steps. So we have a time step of 0.25 and 0.5 for both systems. And we also tested two different initial conditions. I mean, this is just one of the examples of many tests that we did. And the dashed lines are the reference solution. And then in purple, you can see the simple velocity Vallée integrator. And it's already, those time steps are too large for these specific systems, so it's not tracking the reference solution. It's actually accumulating an integration error. And then our Hamiltonian flow map that has been trained on these systems actually, for the same time steps, tracks the solution really well, right? So it's accurate, and it's still using the same large time step. And of course, the ultimate goal is to apply this to real molecules. So here's an example for paracetamol from the MD17 time step. And now we are comparing a traditional velocity Vallée integration, and we compare it with the Hamiltonian flow map that of course can skip time steps, and it's more than 10 times faster. And yet it's still kind of sampled from the same phase space, right? So for the same duration of the simulation, we essentially get a better coverage or better sampling of the Boltzmann distribution. Okay, and and this already brings me to the conclusion. So I was exploring how to use implicit modeling to kind kind of wrap force prediction and DMD simulation into one problem that we want to solve jointly now with machine learning. And the goal was to kind of reduce the complexity that is represented here in the first line. And the first approach was to reduce the prefactor of the machine learning force field by reusing latent representation along the trajectory. And we did this by warm starting. So by warm starting our implicit models. And we discovered that using this approach, we can actually retain the accuracy and stability of existing deep explicit machine learning force fields, but still, at least in the context of an simulation, reduce the complexity. And then the second approach went one step further, where we really wrapped the integration and the force prediction into one model, and this is Hamiltonian flow maps, and it learns the to leapfrog steps directly, and we can train it without relying on reference trajectories, just from the same data sets that we already have generated, that the community has generated for general purpose machine learning force fields. And this, of course, enables simulations at much larger scales because we effectively take less steps to get the time scales. Okay, and now I'm happy to take questions.
Hello, Stefan. Lovely to have you here again. I'm surprised the Hamilton flow map thing works, because in the equation you presented, I think one of the first slides with on the bottom there's a du by dt. Mm-hmm. So what if the du is 0?
Okay, so that's a good question, because there's a little, so I left out some of the important training details. So it's a differential equation and it needs an initial or a boundary value, and the boundary value is actually t0. So we specifically make sure that we actually over-represent samples for t equals 0. And that acts as a boundary condition. So without that, you're right, it's not going to be stable because it relies on this boundary condition.
Right, but what if so U is some sort of?
So U is the neural network.
Right. Okay.
And
the U is never 0.
And no, we just make so we make sure that for delta t0, there's enough training data. So yeah. So that's because that's the current state, and it needs this to kind of start the. I mean, internally, what the model, of course, is also doing, it has to do this, is also doing this integration, right, in an amortized way. So it's more efficient, but it's doing the integration, and it's starting the integration from delta t0, and therefore we need to make sure that during our training schedule, there's enough t0 samples in the training data.
So you say U is just the potential.
Yeah, it's this mean flow map that you see in number 1 in the first. So it's the
right. But so there have to be stationary points where the flow is 0. Would you manage to bring in 0-point energies?
So this, what do you mean? So I'm not sure. So it's not. I mean, the flow is not stationary unless the kind of for general like phase spaces, right? Yeah. So it's not. It's so in principle this could be solved exactly by solving this integral in the first line, but then we again would need to have this trajectory information, which we want to avoid. So we turn this integral equation into the differential equation that you see in number 2. And the differential equation only uses instantaneous values. So it's an equivalent transformation, but it's, so it's not, it's really... Sorry, say again?
Can I just boil it down for me who doesn't fully understand? Just to say, okay, you didn't have stability problems because you chose a boundary condition.
Yeah, so the stability problem, I mean, the stability problems can, of course, in principle appear, but they usually appear from in different ways. For example, the onset of chaos, or then there's also some. Generally, it's a more it's a more difficult learning problem, I would say, than a general force field, because you have this time component. So convergence is a bit more difficult in some cases. But in terms of stationarity of the flow map, nothing that we so far have encountered.
Okay, I don't want to hog your attention. I'm sure there are lots of questions. I just want to sneakily ask, does this sort of map onto parallel? Or can you sort of build momentum effects in there?
I mean, in
a natural way.
I think in spirit, this implicit approach that I've shown first is more close to Parallel, right? So instead of propagating the wave function, we're propagating the internal equivalent, in the machine learning equivalent of the wave function, the internal representation. But I think it's hard to make really rigorous connections.
We have a question from online, from Abraham Mooney, and he's asking, is there any situation where the embeddings in the implicit MLFF doesn't converge, or where convergence doesn't necessarily bring you to the true state? And if so, how do you deal with those cases?
Yeah, so actually we control, well, I said that this the layer that we use to create the implicit model, it needs to satisfy a few properties, and one of them is that the convergence radius needs to be bounded, so there's some normalization necessary, which is quite trivial, and once this layer is normalized, we know that there is a fixed point. And then the other, there's another challenge of uniqueness, so can we ensure that the fixed point is unique? Currently we don't have a constraint for that, right? Which in practice is not really a downside, but you would like to have, I mean, ideally you would like to have an implicit model or fixed point equation that only also has one solution, because then there's no surprises. But so far, empirically, it's still stable.
Have time
There's two more.
Yeah, so a question about these Hamiltonian flow maps. So the dynamics of your system depend on the ensemble you're sampling in, or the conditions in which you're sampling. My question is then, are these models then trained purely on one specific set of conditions, one temperature, one pressure, or can these be inputted also as a descriptor, as an input descriptor?
Mm-hmm. Yeah, also a very important question. So indeed, currently, I mean, we're sampling from a Maxwell distribution of momenta. So it's kind of it gets all in training data. We have like a distribution of momenta and then the exact positions from the training set. And in terms of terminalizing the simulation, that's a bit more difficult. Because if we wanted, or well, we do apply in the thermostat, but it can obviously only act on the simulation step, on the large simulation step. So there's going to be some inaccuracies in that regard. In the long term, a possible way to fix this is to use a recent development that is called stochastic flow maps, which could in principle incorporate this the thermostat into this model, but currently we're limited by applying the thermostat from the outside.
Okay, last question.
Thank you for a very interesting talk. So how far can you push this? Can you now simulate a fully solvated protein for milliseconds?
No. So, I mean, so there's this I mean, first of all, you're limited. You have to stay within the deterministic regime of the MD simulation, right? And usually, so empirically, we know that for those small molecules that we are considering in those tests is about 100 femtoseconds, which is like 200 times more than the traditional time resolution. And we even only do around like 20 femtoseconds, or I think 17 in this animation that you've seen. So this is where the model remains stable. When doing some, so essentially, so this is kind of, so the horizon is the deterministic limit of the simulation. And we are hoping that we can push it towards closer to this 100 femtosecond regime, but it's going to be about the limit.
Okay, thank you very much, John. Yeah.